So let's look at the next topic, which I'm calling mu1 plus mu2, which is really my way of saying multiple decrement models. Okay, I'm not going to go through all the notation for multiple decrement models. I'm just going to go through the central conceptual thing, the central calculus of multiple decrement models, i.e. there could be two different things going on. There could be both death and serious injury, or both death and retirement, or something like that, or just different events that might happen that might cause you to drop out of a population for some reason or another. The central issue, the central calculus of it, is that you add the forces of mortality together. Okay, so first thing we're going to look at force of mortality, okay, which is the equivalent of force of interest, and then we'll move on to looking at how we look at multiple decrements, like multiple causes of mortality or multiple causes of some other decrement in some other way. If you think about the force of interest, the delta, it's really the way we come across that is in the context of the value of money decaying over time. So you have e to the minus delta times t, and that is saying that delta is the rate at which the value of money decays over time. Okay, well, in mortality world, we tend to have sort of px is the probability they're alive after 1 year, 2px the probability they're alive after 3 years, 3px is the probability they're alive after 3 years. Okay, and the reason why we tend to use the discrete 1 year, 2 year, 3 year most of the time is because the tables, as we've just seen, give us the data in discrete 1 year at a time. Okay, but that doesn't mean that underlying that we can't think of it in a more continuous way. Okay, and that gives us this great concept, the mu, okay, the force of mortality. And the force of mortality reduces exponentially the number of lives, or the probability that a life exists. Okay, so if we have a constant mu, and most of the time when you're dealing with actuarial problems in the exams, the mu's will be constant, otherwise the math just gets too complicated. So for a constant mu, tpx, the probability we are alive t time in the future, if we're currently aged x, is simply e to the minus mu times t. Okay, so it's just your standard exponential decay, and that's it. That's all you really need to understand about mu. We typically see the tables, the mu's will be tabulated for each year. Just find the mu's, all sorts of nonsense you don't need to worry about. So here we go, so that's the select mu, and this is the standard mu. So okay, so they're tabulated for each year, and that is what that's doing, what that number there is doing, is saying assume the force of mortality is constant between the age of 65 and 66. It's making that assumption and calculating what it is. Okay, so the form you would more often see is we think that the mu is constant each year but changes. It's different each year but is constant during the year. So that sort of means the notation develops to mu 65, for example, is equal to, sorry, I don't mean to do that. So if we want mu 65, we want to know what mu 65 is, and I only remember a formula one way around, okay? I only ever remember this formula this way around, okay? Because mu is an exponential decay, so its place is to be here in the exponential. That's where you get your exponential decay. So don't start remembering the formula in log 1 minus this or that. You can work that out. You can do the algebra to work that out. You don't need to remember that. So all I've got to remember is that the mu goes there. In that case, if I want mu 65, then I must be dealing with 1p65. The probability of dying in 1 year is e to the minus mu 65 times the time, which is 1. Okay, and now I can rearrange that log of 1p65 minus equals mu 65 if I want to work out what the individual mu is if I know what the different values of Lx are. And of course, if I want to know what 1p65 is, or p65, I can write abbreviation, that's just L66 over L65. So that's all the force of mortality is. Then, what do we do when we have different things? So let's give you an example. We're going to look at the probability of dying of cancer and the probability of dying of heart disease in a year. Okay, so supposing, as an artificial example, so we start off with a world that has no cancer and just heart disease. Okay, there's no cancer, but there is heart disease. And the force of mortality at age 65 for heart disease is 0.04. Okay, so this is the only form of death. So what is the probability that you survive 1 year? Okay, well, P65 is e to the minus 0.04, which is equal to I apologise, I didn't switch the recorder on again, so I've gone slightly out of sync. So P65 equals e to the minus 0.04 is 0.96079. So that's the probability we survive 1 year if the only form of death is heart disease. Okay, but then we bring cancer into the population, okay, and it's known that mu65 for cancer is 0.1, okay. How do we work out what the probability of death is over the year when we've got a force of mortality from heart disease of 0.04 and a force of mortality from cancer of 0.1? And the answer is extremely simple. You add the forces of mortality together. You do not add probabilities together. This is the amazing thing about this. They're interacting, they're probabilities which are interacting, but if you add the forces together, it works perfectly well. Okay, so if you add both together, the force of mortality for cancer and the force of mortality for heart disease, then you find that you can work out the total probability of death, and the total probability of survival there is 0.86936, okay, which is the probability of death is less than the total probability of death if you added the two probabilities of death together. Okay, so that's all you need to do. To check that, let me do it with a slightly different, I'll do it with heart disease and cancer again. Okay, and let me do it with slightly different numbers. Okay, so let's say the independent prob of heart disease death is 20%. So that's the probability of death. Okay, the independent probability of cancer death is 10%. Okay, so your chance of survival from heart disease, your independent chance of survival, heart disease, is 80%. Your chance of survival from cancer is 90%. Okay, so your total chance of survival is 0.8 times 0.9, which equals 72%. Okay, and these are the two independent things that can take you out in a year. You've got an 80% chance of surviving one and 90% chance of surviving the other. The total chance of survival is 72%. Okay, so the total probability of death is equal to 28%. How do we get 28%? from these two probabilities. Okay, well, it's a bit tricky. We have to do it by this method, which is 1 minus P1 times 1 minus P2, effectively. But let's have a look at forces of mortality. Okay, so we assume that there is a constant force of mortality. Okay, so for heart disease, we have the probability P, whatever age, Px1 is equal to 0.8, okay, which is equal to e to the minus mu heart disease. Therefore, mu heart disease equals minus log of 0.8, which equals 0.223144. Okay, now do cancer. Again, just to reiterate, there is all sorts of notation I could be showing you now, but it really just doesn't really help you understand it. Okay, so mu cancer equals minus log 0.9. Which is, and you notice these things are non-linear, so it's amazing in a way that just adding the mu's together work, but this should satisfy you that that is the case. Okay, and I'm saying the total probability of survival, okay, so 1px heart disease, 1px cancer total is equal to e to the minus mu heart disease plus mu cancer times t, which is 1. Okay, so what's that equal to? E to the minus 0.223144 plus 0.105361. Okay, so that is sum of those two numbers equals that plus that, then equals exponential minus that. And hey presto, we've got our 72% that we could see directly was the answer. But we've done this by looking at the constant force of mortality. So to show that the forces of mortality are additive. Okay, so forces of mortality are additive, and this thing extends. The other great thing about force of mortality is it extends into variable force of mortality as well. Okay, so we can say that for constant force of mortality, the probability of survival is e to the minus mu t. Okay, but in general, just like with the force of interest, that is the integral of mu between 0 and t. Okay, so I can extend this thing when it's variable mu, so mu is a function of t, or of a function of age. So it's better make that. Let me get rid of that. So mu is a function of age, which is you naturally expect it to be. In fact, it will be. So now I can do Tpx is equal to e to the minus the integral between 0 and t of the force of mortality as a variable, which here is going to be x plus whatever the integrating variable is. Let's call it tau, d tau. Okay, so that seems like, ooh, that looks a messy formula, doesn't it? That looks difficult and complicated, that. But actually, all you're doing is thinking mu is the exponential decay of survival. Okay, so that is how you write exponential k of survival. That there is your very simple A-level math exponential decay of survival. Okay, so you generalize that and you get for variable mu. Okay, so sometimes questions you just tee it up like that and think, well, that looks difficult, but you know, if mu is linear, it might be, rather than constant, it might be linear. Well, that's still easy enough to integrate. Or it's quadratic over a short period, that's easy enough to integrate. Okay, or it may be exponential. In fact, it probably is largely exponential. If you actually look at how mu works, it increases by, with each year of age, it increases by about 8%. The force of mortality. So that is quite a decent way of looking at it, and you can then you can fairly easily integrate this function if this function is exponential. So yeah, you know, you can do all sorts of things like that. But that's really how to think about the force of mortality. So in fact, let's do an example. Okay. So supposing, oops, so suppose mu of x is equal to 0.0001 times e to the x over 10. Okay, so that's the force of mortality at any given age. And we want to calculate 10p40. Okay, so 10p40 equals e to the minus 0 to 10 mu of x plus 40 plus t dt. Okay. So that is equal to e minus integral between 0 and 10 of 0.0001 e to the 40 plus t over 10 dt. Okay, which is e to the minus 0.0001 comes outside the bracket, e to the 4 comes outside the bracket, integral between 0 and 10, e to the t over 10 dt equals e to the minus 0.0001 e to the 4 times integrate that, so 10 e to the t over 10 between 10 and 0. Which equals e to the minus 0.0001 e to the 4 times by 10 e minus 10 times e to the 0, which is times 1. Okay, so then we just work that out. Equals minus 0.0001 times exponential 1, sorry, e to the power 4, just do exponential 4, times open bracket 10 times exponential of 1 minus 10. Okay, so that is the exponent, so I want equals exponential of that, and I get 91.04%. That's my probability of survival. So pretty straightforward, really. And for the whole of multiple decrement models, all you really need to just, I'd always go back, convert it into forces of mortality, go back, do your analysis with forces of mortality being additive, and then reconvert it back to probabilities. There are a whole set of shortcuts with sort of halfway across this and divide by that, and it really doesn't help. It just makes it massively overcomplicated. The fundamental calculus of multiple decrement models is that the mu's are additive. Okay? It comes down to the fact that probability of A or B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Okay? But when you're dealing with mu times dt, an infinitesimal, that is an infinitesimal, the actual probability you're dealing with is infinitesimally small, okay, then this disappears. So that is why the calculus of multiple decrement models works by just adding the mu's together. If you try and do it with actual probabilities, you've got to use this kind of relationship, okay, which is why it's tricky, because you then got to go back to multiplying the probabilities of the complement event. So if the cancer survival is 80%, the heart disease survival is 90%, to work out the probability of surviving both, you've got to multiply both those survival probabilities together. So if you've just got the probability of dying from either, it becomes quite complicated. If you do it with the mu's, if you just add the mu's together, the thing becomes perfectly straightforward. Okay, so that is the end of multiple decrement models. That's all we need to know about it, really.